So let's talk about how we can get around this issue. The, the problem that we're encountering is that when we change coordinate systems, we're actually stretching our axes. So in our first example where we changed coordinates to integrate over a square rather than a parallelogram, we saw that the calculation we ended up doing gave us the answer, but we were off by a factor of the area of the region. So let's take a closer look here. So whenever we're changing variables, the archetype is something like this. We introduce new variables, maybe we can innocuously call those variables u and v for the moment, and then we use some function from R2 to R2 in this case, where the input for this function capital T are those variables u and v, and the output are the variables we start with, x and y. And the idea is that when we do this, what we're doing is we're sort of contorting the original coordinate system. So if we're working with squares in the UV world, we end up working with sort of like tilty or wavy objects in the XY world. So the idea here is that we're actually stretching our axes when we change variables. So the issue that we're encountering here is that we want to relate two integrals. The integral we care about is the double integral over the region D in xy space, where the density function is f. Well, the problem that we're encountering is that the region we're studying might be difficult to set up this integral over. So we change our variables, and then we look at this new integral where we take our density function and compose it with the change of variables. And technically what that amounts to is just replacing the x's and y's with the appropriate formulas in terms of u and v. And the idea is that the new domain we're working with, d star, gives us an easier calculus problem. So we want to relate these two integrals, but to do this, what we actually need to do is account for how the change of variables stretches our coordinate systems. So let's take a closer look at the geometry here. So if we're stretching coordinate axes, what we're really doing is we're adjusting area. So in UV space, if we were to look at like a small square where the change horizontally was given by some quantity delta u, and the change vertically is given by some quantity delta v, we can think about what happens when we apply the change of coordinates t of uv. And the idea is that, well, the delta u is manipulated in the u direction by the partial derivative of our change of coordinates with respect to u. And our delta v is manipulated by the partial derivative of t with respect to v. So this is accounting for how the area is changed after this change of coordinates. So maybe if we wanted to be more formal about it, the idea is that areas in two dimensions are measured by determinants. So what is this telling me? Well, if we look at this figure to the right, what we're looking at is the region D, where the actual region itself has a sort of contortion to it. But if we look at the partial derivatives as vectors, t sub u and t sub v, we're looking at a small parallelogram that approximates the area of that region. So what we get is an approximation. Change in the x direction times change in the y direction is approximately equal to the area of this parallelogram multiplied by the original changes in u and v. And the area of that parallelogram should be the determinant of the matrix whose columns are the partial derivatives of t with respect to u and the partial derivative of t with respect to v. And this is an approximation that works for small regions. To get into a precise answer, we should take limits. And when we take limits, what we end up with is a formula that says dx times dy should be equal to the absolute value of the determinant of the matrix whose columns are the partials of the change of variables function with respect to its input variables, multiplied by du dv. This tells us why we were off in the motivational examples. we weren't accounting for the stretching of area when we change variables. So of course we got an incorrect answer. In order to get a correct answer, we have to precisely relate dx times dy to du times dv. And this area idea says the appropriate factor is the absolute value of the determinant of this matrix. So let's introduce some formalism here. Let's say we're studying a transformation capital T from one region D star to another region D. So this is the same visual we had from the previous slide. We define what's called the Jacobian determinant of this change of variables, notationally as follows. So we're using fractional notation here, where in the numerator we're using the partial derivative symbol, and then we're inputting x and y, because we're envisioning that t spits out the variables x and y. And then in the denominator here, we're writing partial derivative symbol of u comma v, where u and v represent our new variables here. This notation stands for the determinant of the Jacobian derivative of the change of variables function. So we've seen the Jacobian derivative many times at this point. For any function from Rn to Rm, the Jacobian derivative is an m by n matrix. Well, in this example, or in this idea, t is really a function from R2 to R2, so its Jacobian derivative is a 2 by 2 matrix, and therefore, since that matrix is square, we can take its determinant. If we take a closer look at the entries inside of that matrix, we see that the first column represents the partial derivatives of the functions x and y of u and v with respect to the variable u. And then the second column gives us the partials of x and y with respect to v. So the Jacobian determinant of this change of variables function is this 2 by 2 determinant. So let's just look at some examples or an example of taking a Jacobian determinant. Here we're introducing a change of variables function. This is t of uv equals the vector in R2, where the first coordinate is u squared times v, and the second coordinate is u minus v. Well, here what we're doing is we're saying that the first coordinate, u squared times v, should be set equal to x, and here we're suggesting that the second coordinate, u minus v, is what we're setting equal to y. Well, what is the Jacobian determinant? Well, again, the symbols say we're using fractional notation, where the numerator is given by the partial derivative symbol with x and y, and then the denominator is the partial derivative symbol with u and v. So this is the determinant of the Jacobian derivative of this function from R2 to R2. And the first column should be the derivatives of x and y with respect to the first input variable u, and the second column represents the derivatives of x and y with respect to the second input variable v. So we need to fill this matrix up with its 4 entries. The partial derivative of x with respect to u is 2 times uv. The partial derivative of y with respect to u is equal to just 1. The partial derivative of x with respect to v is equal to u squared. And the partial derivative of y with respect to v is simply equal to -1. So those are our 4 entries in our matrix. And remember, to take a determinant of a 2 by 2, we simply multiply the diagonal entries and subtract the product of the other 2 entries. So here we end up with -2 times uv minus u squared. So that's the Jacobian determinant of this particular function. One thing I want to point out, which will become useful later, is that if we invert the Jacobian determinant, well, that would be looking at the partials of u and v with respect to x and y. And this would be a difficult problem if we tried to do this from scratch, because we would have to solve for u in terms of x and solve for v in terms of y. But if we have an understanding of the linear algebra in the background here, we realize that we don't really need, if we wanted to solve this problem, to solve for u and v in terms of x and y. Instead, what we can do is we can just invert the Jacobian derivative that we just calculated. So what we could do instead is really just take 1 over partials of xy with respect to uv. And so that would be 1 over the quantity we just calculated, negative 2 times uv minus u squared. The rule that allows us to do this is technically called the inverse function theorem. So this is one of the fortunate aspects of the notation we're choosing, because what this is saying is that the thing that we would sort of maybe want to do when finding partials of u and v with respect to x and y is really just take 1 over this fraction flipped. And what this inverse function theorem is telling us is that from the calculus actually supports that notation. Okay, so now we have enough of the language we need in order to state the change of variables formula. So the setup is, let's say we're studying a transformation capital T from one region D star in UV space to another region D in XY space. So the idea here is that we're starting with this region in the XY space D, and at some point in our problem, we decided to introduce a change of variables function called T that relates this region D star to this region D. Well, before what we were doing is we were being a bit too naive. We were taking our density function, measuring density inside of D, and simply replacing the x's and y's with the appropriate u's and v's, and then integrating in UV space. What we saw was that even though this idea gave us easier calculus, it was throwing our answers off. It turned out that what we were missing was this ingredient of the Jacobian determinant. So here's the technical statement. The double integral of a density function f of x and y throughout the region D is the same thing in this scenario as a double integral over the region D star in UV space, where the function we're integrating is the function f, but we replace the x's with u's and v's and the y's with u's and v's. And then we need to multiply by the absolute value of the Jacobian determinant of the change of variables function. And so by multiplying by this absolute value, what we're doing is we're accounting for how area is stretched under this change of variables. So this completes the picture, and this answers the question. So where this ends up being useful is when we start with this integral on the right, and this integral is difficult, so we introduce a change of variables to make the problem easier, and what we end up doing is we replace the x's and y's with the appropriate u's and v's, and then to account for the stretching, we multiply by the absolute value of the Jacobian determinant, and then we can solve our problem. So let's see an example here. Let's go back to the parallelogram that we started this lecture with. In that problem, the function measuring density was 3 times x squared plus y, and the region we were studying was the parallelogram spanned by the vectors 1, 3, and 1, 2. Well, what we did previously was we introduced a change of variables function by looking at the matrix whose columns were the two vectors defining this parallelogram, and that related the unit square in UV space to the parallelogram of interest in XY space. So we can now calculate the mass of D by using the change of variables formula. Instead of integrating over the region D that we're interested in, let's integrate over D star, which has a nicer description. So now, instead of doing 3 iterated integrals, we only need 1. Here, the u's and v's are both ranging between 0 and 1. The function we're studying is 3 times x squared plus y, but now we're replacing x by 3u plus v, and we're replacing y by u plus 2v. We also need to account for the Jacobian determinant, which ends up being 5 in this case. So in our integrand here, to use the change of variables formula, this portion in the curly braces is equal to the value of f of xy, where x is replaced by 3u plus v, and y is replaced by u plus 2v. And this 5 is the Jacobian determinant, or the absolute value of the Jacobian determinant of the change of variables function. When we look at the change of variables here, we see that the derivative of x with respect to u is 3. The derivative of y with respect to u is 1. The derivative of x with respect to v is 1. And the derivative of y with respect to v is equal to 2. So now when we take the Jacobian determinant here, we end up with 6 minus 1, which is 5. Now when we do the calculus, we end up with 80 kilograms, which is exactly the answer that we knew previously. Let's look at another, maybe more complicated example. Here we're looking at an example where the region D we're studying is bounded by these 4 curves. So this is a complicated region that's bounded between these 2 lines and these 2 curves. So here what we see is the lines in this region are y minus x equals 0 and y minus x equals 2. And the curves defining the other sides of these regions are x times y equals 1 and x times y equals 4. So we have a density function and we have a region. Again, the goal here is to calculate mass. And the problem with this region is that it's quite complicated from an iterated integrals perspective, because if we were to set this problem up using our x's and y's, we would need 3 iterated integrals. Because if we take a vertical slice between this juncture and this juncture, we have one rule for entry and a rule for exit, but the rule for entry changes when we pass this juncture. And then when we get to this juncture, the rule for exit changes. So we would have a complicated iterated integral on our hands if we were to do this directly. So instead what we want to do is we want to invoke this idea of change of variables. The clever thing to do here is to note that the formulas defining the bounds for this region have commonalities. 2 of the bounds are y minus x equals 0 and y minus x equals 2. And the other 2 are x times y equals 1. And then that same expression, x times y equals 4. So what this is really doing is it's suggesting that maybe there's a convenient new coordinate system we can work with. Let's set our first new variable u equal to y minus x. And let's set our second variable v equal to x times y. With this perspective, we could look at the Jacobian determinant of the x's and y's with respect to the u's and v's. But the important thing to point out here is that the way we're introducing our variables for this problem is not to set x's and y's equal to particular u's and v's. It's to introduce these new variables, u and v, because they conveniently match the description of this region. So if we were to use the change of variables formula, we would need the partials of x's and y's with respect to u's and v's, but I don't have convenient access to that data because I haven't solved x and y in terms of u and v. The example we did previously, where we mentioned the inverse function theorem, tells us exactly how to bypass this issue. The partials of x and y with respect to u and v should be the same thing as 1 divided by the partials of u and v with respect to x and y. And we can calculate the partials of u and v with respect to x and y here. The partial of u with respect to x is negative 1. The partial of v with respect to x is equal to y. The partial of u with respect to y is 1. And the partial of v with respect to y is equal to x. We can take this determinant in the denominator, and we end up with the quantity negative 1 divided by y plus x. So now we're set to use the change of variables formula. The mass of this region under change of variables says, well, instead of working with the x's and y's, why don't we work with u's and v's? If u is y minus x, then throughout this region, u is ranging from 0 to 2. So our new integral is du, where u ranges from 0 to 2. And if v is equal to x times y, then v is ranging from 1 to 4. So the second bound in our integral, dv, is 1 to 4. And what are we integrating here? Well, we're supposed to integrate our density function, which was given to us as y plus x multiplied by y minus x. And then to account for the stretching that occurs when we change variables in this way, we need to multiply by our Jacobian determinant, which in our example, partials of x's and y's with respect to u's and v's was -1 divided by y plus x. And in the formula for change of variables, we always take an absolute value of this quantity. So our -1 becomes a +1. And then we can see here that someone took care to write this problem cleverly, because now this y plus x in the density function cancels with the denominator of y plus x coming from the Jacobian determinant. And what's left over here is this factor of y minus x, but in our change of variables, we said that y minus x was simply equal to u. So now our integral massively simplifies. We're integrating u du dv, where u ranges from 0 to 2, and v ranges from 1 to 4. We can easily do the calculus here, and we get an answer which is equal to 6 kilograms.